Here we have an example. Shown in the figure are two ends of long straight wires that are parallel to each other and perpendicular to the xy plane. Each wire is carrying a current but in opposite directions. Find the magnetic field at points P1, P2, and P3. Find the expression for the magnetic field at any point on the x-axis to the right of wire 2. Using the right-hand rule we figure the direction of the magnetic field for each wire. We see that they rotate in the opposite direction. We change its view to side view to better solve the problem. The first wire, its current is moving out of the page as indicated by the purple dot, and its magnetic field is rotating counterclockwise. For the second wire, the direction of current is going into the page as indicated by the purple cross, and its magnetic field is rotating in clockwise direction. The positions are indicated here also. The magnetic field at any point by different sources is simply the sum of these fields. The net magnetic field is given as equation 1. In this case we expect that the net magnetic field is going downwards because the first wire is closer and it has more push towards the counterclockwise direction, thus greater magnitude in the downward direction. The distance r equals 2d since it is the distance between the wire and point 1. It has a direction of j since it is pointing downward in the y-axis. For wire 2 we have equation C. The distance r equals 4d since it is the distance between the wire and point 1. The direction of j is positive since it is pointing upward in the y-axis. Summing the two fields we have a net magnetic field at point 1 where it is a negative value, mathematically proving that it is pointed downward as shown in equation D. For point 2, the magnetic fields are both pointing in upward direction with respect to the y-axis. Since they are both equidistant, then they both have the same expression for the magnetic field and it is given as equation A. Then the net magnetic field at point 2 is given as equation F. For point 3, the direction of the magnetic fields are opposite to each other, same in point 1. For wire 1 where we write it in vector form we have equation G. The distance r is equal to 3d since it is the distance between the wire and point 3. It has a direction of j hat positive since it is pointing upwards in the y-axis. For wire 2 where we write it in vector form we have equation H. The distance r is equal to d since it is the distance between the wire and point 3. It has a direction of j hat negative since it is pointing downwards in the y-axis. The net magnetic field then at point 3 is given as equation I. For the case where we write an expression for the net magnetic field at any point on the x-axis to the right of wire 2, we look at the figure. We let point x be that position on the right side of wire 2, so the distances with respect point x from the perspective of wire 1 is given as equation J. Then the magnetic field due to wire 1 is given as equation K. For the second wire the distance is given as equation L. The magnetic field due wire 2 is given as equation M. The net magnetic field is then given as equation N. This is the net magnetic field at any point on the x-axis to the right of wire 2.